3, 2, 1. Okay, Archimedes principles next up. We're again dealing with water or liquid issues. We're going to discuss the importance of buoyancy. Buoyancy is the liquid pushing up against gravity until equilibrium is established. So whatever object you drop in there, the force or the pressure of the force of the water is going to push up, and the object is going to push down until they have an equal equilibrium established there. And from that, whatever water is displaced, that's going to be the volume of the substance, and we're going to figure out what to do with it when we get to that point. So buoyant pressure and gravitational pressure are going to be the same. Now, we've already discussed the relationship between pressure, volume, and area. So P equals F over A, and we're going to look at it in two aspects: buoyant pressure and gravitational pressure. And we are also going to bring in the definition we have for pressure from the previous lesson, where pressure is density times G times H. And we look at the change of pressure. The density and the gravitational acceleration stays the same, but the height changes. So if you have a change in pressure, it's going to be dependent upon the change in height. And that becomes real important in how Archimedes comes up with this idea about being able to determine what the buoyancy force is going to be. Okay, so PB equals dgh. FB, then if you multiply by A here, gives you dgHA, that's density, gravitational acceleration, the height or the change in depth, whatever you want to call it, and the area. Okay, now, since volume equals height times area, we can replace height times area with volume. So buoyant force is equal to dg times volume. And again, these two are constant for water, but it will not be constant for the weight, so we'll come to that as well. So at equilibrium, the buoyant force and the gravitational force are the same. And the gravitational force is m times g, and that's what we call weight. We used to call it Fw, but I want to reinforce the gravitational aspect of this. That is the weight of the volume displaced of the water. That is Archimedes' principle. So whatever the weight of the water that comes out, we can measure the volume from that, and then we can figure out what we're going to do with find the density of the material that we're dealing with here, or other things, as is the case here. The example here is we have a spherical balloon with a radius of 0.750 meters. And it's filled with helium. The density of helium is 0.180 kilograms, not kilometers. That should be kilograms per cubic meter. So two things we want to find out: what is the buoyant force, and what is the and if the mass of the balloon weighs is 3.55 kilograms, what is its acceleration? Okay, so the results for that. For the first one, we're trying to find the FB. FB is defined as dgV, density, gravitational acceleration, volume. The density of helium is 0.180 kilograms per cubic meter. The gravitational acceleration, 9.80 meters per second squared. And the volume of a sphere is 4/3 pi r cubed. And the radius is 0.750 meters, and we're cubing that whole thing times 4/3 pi. And we get 3.12 newtons. Then the second thing that we're asked to find out was what is the acceleration of that balloon as it starts to go up. And since force is mass times acceleration, then we can find out acceleration by taking the force divided by the mass. Well, we know the force of the balloon going up is 3.12 newtons. We know that the mass of the balloon is 3.55 kilograms, so it's going to keep it from going up at a very high speed. It's going to slow it down quite a bit. And that ratio then gives us 0.879 meters per square centimeter. So that's how we can figure out how fast an object that's lighter than air in a balloon will actually be able to work. That's buoyancy of the helium against the air. Now, in this situation here, in this example, we're taking some kind of weight. We're putting on a scale. The scale is in the water. We know that when we weighed before we put it in the water, it was 9.5 newtons. In the water, it was 4.5 newtons. So that means the force of the spilled water was 5 newtons, or of the spilled object. That's not really water, but the water of the spilled is 5 newtons. So we can figure out the density from that. That's what we're trying to find. We now are going to find the volume of the water that came out with 5 newtons divided by the density times the gradual acceleration. We have 5.10 times 10 to the negative fourth. And then change that to liters, and then change that to cc's. We get 51.0 cc's. The mass of the object is the force divided by the force divided by the density. That should be density right there. And this is going to be 9.50 newtons divided by 9.80 meters per second squared. It gives us 0.969 kilograms, which is 969 grams. So we take 969 grams divided by 51.0 cc's. To get the density of the object, we get 19.0 grams per cc. Now you've seen all 3 types of problems. Get to work and have fun!